Okay, in this video, we're going to take a look at the Laplace transform of y prime of t, of a derivative. And here's where we're going to see that we start with something that definitely has calculus in it. That's the derivative of y. When I take the Laplace transform, what I'm going to write here eventually, there's not going to be any calculus in it. That's just going to be an algebraic expression in terms of capital Y of S, which is the Laplace transform of y. Okay. Now, of course, in order to figure out what that is, I need to do some calculus, but this is going to allow me to go from something that has calculus in it to something that just has algebra in it. Okay, so if I'm taking the Laplace transform of y prime of t, definition is that that's the integral from 0 to infinity of y prime of t times e to the negative st, integrating with respect to t. Okay. And of course, that means y and y prime need to be functions that are defined from 0 to infinity, and remember that have no more than exponential growth. What that means is that eventually, for t big enough, this piece is going to dominate. So this piece is going to 0, it's going to drag this piece with it, so eventually this thing goes to 0 so that this improper integral will converge. Okay. Of course, the way I do any improper integral is I rewrite it as a limit. So I'm going to let it be the limit as b goes to infinity. Nothing sacred about the symbol b, but I'm so used to integrating from a to b that since my variable is going to be my upper limit of integration, I just let it be b. So we're going from 0 to b of y prime of t times e to the negative st dt. So if I look at what I'm integrating here, it's a product of two functions. And since I don't have an explicit formula for y prime, I don't know if it has any nice connection to e to the negative st. So I don't know if I can simplify that before I integrate, or if the u sub will work. I want to think, what do I usually do when I'm integrating a product? And that's going to be integration by parts. So I'm going to just write up here, remind us what the formula is. If you're doing a definite integral from a to b of u times v prime with respect to t. So I'm integrating a product and I'm viewing one factor as a function and the other factor as the derivative of some function. What I get is u times v evaluated between b and a minus the integral of u prime times v. This is also from a to b dt. So essentially what's happening is this is undoing the product rule. This would be one of the two terms that would show up in the derivative of the product if I were to take the derivative of the product of uv. So when I integrate one of those terms, I get the original product minus the integral of the other term that would show up in the product rule. One thing that's very important, people often forget when it's a definite integral that both pieces are affected by these limits of integration. I don't get the function uv, I get uv evaluated at those limits of integration and subtracted. Okay. All right, so I have to figure out which one of these I want to be u and which one I want to be v prime. I'm thinking I want that to be my v prime because the one that's the derivative, I'm going to have to find an antiderivative of. And an antiderivative of y prime would just be y. Okay. So I'm going to let u be e to the negative st. My v prime will be y prime of t. So then I need to know u prime. That's going to be negative se to the negative st. And v, an antiderivative of y prime, would just be y. Okay. All right. So with that choice, I can now say this is the limit as b goes to infinity of u times v is e to the negative st times y of t. We've got to evaluate that between b and 0. And then I've got to subtract the integral from 0 to b of u prime times v. So that would be negative se to the negative st times y of t dt. Okay. And I can see the negative signs here will just cancel each other out. Okay. All right, I'm going to just split up the limit into two pieces because limits distribute over addition. So this is going to give me the limit as b goes to infinity of e to the negative s times b times y of b minus e to the 0, which is just 1, times y of 0. Plus, I can factor out the s because for the purposes of this integral, s is a constant. So I get limit. I was distributing the limit. Limit as b goes to infinity. Integral from 0 to b with that s factored out, e to the negative st times y of t dt. So, let's evaluate this limit. Now, remember, we said that this function was going to have no more than exponential growth, so that eventually this term was going to dominate. If I wanted to, I could rewrite e to the negative sb times y of st times y of b as y of b over e to the st. B may be going off to infinity so that this piece is getting big, but we said eventually, when my input to y gets big enough, eventually exponential functions are going to dominate. So this piece going to 0 drags the whole thing with it, or equivalently, even if this piece is big, I'm getting a fraction where this piece is way bigger, it wins. So this term is going to go to 0. So what I get is negative y of 0. Notice that's just my initial condition. Okay, plus I can actually pull the s outside of this limit, but let's take a look at what we have. We have the limit as b goes to infinity of the integral from 0 to b. So that's just an improper integral from 0 to infinity. And take a look at what I'm integrating. Y of t times e to the negative st. That's exactly the Laplace transform of y of t. So, if I apply the Laplace transform to a derivative, I'm just going to write this term first. I'm going to get s times the Laplace transform of the original function minus y of 0. Derivative, that's calculus. Multiplying by s and subtracting a constant, that's just algebra. Okay. So we've gone from an expression involving calculus to an expression just involving some algebra. If I wanted to, I could write this as s times y of s. Remember, when we apply the Laplace transform, we generally keep the name of the function but make it a capital number. And of course, the Laplace transform of a function of t becomes a function of s, and then minus y of 0. Now again, that's my initial condition. So you might say, oh, do I have to have an initial condition to use Laplace transforms? The answer is no. If you do, you will have a specific number to plug in here. If not, this is your arbitrary constant. We're used to, when we work with differential equations, an arbitrary constant shows up sometimes. This arbitrary constant just has a specific meaning. It's going to be what the value of y is at time 0. And if we think about it, when we're solving an initial value problem and we have some arbitrary constants, we use the initial condition to figure out what those arbitrary constants are. So there's always a connection between the initial condition and the constants that show up in my equation. Here it's just a very explicit connection. That constant is the initial value of my function y.